Finally, our last video for types of radioactive decay, video number 4. What we'll be focusing on for this one is going to be called electron capture. Electron capture is exactly what the name sounds like. The nucleus is going to absorb or capture one of its electrons, and then it's going to be attracted, because electrons are negative, it's going to be attracted to the proton in the nucleus, because positive, negative are going to attract. So that nucleus is going to suck in one of its electrons, and that proton is now going to change to a neutron, because now you have that one positive, the one negative, and it'll become neutral. The symbol for this is the same as the symbol for a beta particle. So because it's talking about an electron, it has no mass, and it does have that -1 charge. So the symbol will remain the same, but we're going to see how, even though they contain the same symbol, it's still going to look different. You'll still be able to identify it in a nuclear reaction. So what is going to change? Because we're capturing that electron and that proton is going to become a neutron, we're once again going to decrease the atomic number by 1, just like we did in positron emission. All right, so except we're doing the opposite here. We're taking an electron and sucking into the nucleus. So we're going to decrease that atomic number by 1. Once again, the mass number remains the same. So we're just turning a proton into a neutron. Same example, 5 and 5 is equal to 10, 6 and 4 is equal to 10. So the mass number is remaining the same. If you notice, throughout all of these videos, the only time the mass number changed was in alpha decay. Otherwise, in every other one, beta decay, positron emission, and electron capture, those mass numbers all remained the same. In every single type of radioactive decay, we did change the atomic number. So in every single type of radioactive decay, we change the element, because we're changing the atomic number. Some examples of electron capture. And this is where you'll see how it's different than all the other ones, because you'll notice right here is where the beta particle is located, or the electron, I guess, is located. So if we look at this, we'll notice that this is different because this is the only one in which there is something else in the beginning of the reaction besides just the element. So in every other one, we started with just the element, and then it turned into another element plus an alpha particle, or another element plus a beta particle, or another element plus a positron. In this one, this is the only one in which we have 2 things in the beginning of the reaction. So for this particular example, we're starting with chromium. So we have 51 as our mass number, and 24 is our number of protons. So therefore, that means we had 27 neutrons. But what it's going to do is it's going to suck in one of its electrons, and one of those protons is going to change to a neutron. And so now we're going to have 23 neutrons. So now we're going to become vanadium. And the mass number, once again, is remaining the same, because electrons have no mass. Even though we added it to the nucleus, the electrons have no mass to them. So 51 and 0 is 51, matches the 51 over here. The number of protons also matches up. We have at 24 plus -1, which would give us 23, which equals the 23 over here. So our numbers are all good to go. Another example of electron capture. We take our helium here, and we'll notice that helium, the mass number is 3, and the atomic number is 2. So we have 1 neutron in this particular atom. And when it undergoes electron capture, it takes in one of its electrons, its own electron, doesn't take it from anybody else, it takes in its own electron, and now it's going to become hydrogen, because it had 2 protons, but that electron gets attracted to the proton, causing it to become neutral. So then it's no longer can be a proton, now it's a neutron. And because we have 1 less proton, now we only have 1 proton total, now it's going to be hydrogen. Mass number, once again, remains the same. So that is electron capture. The biggest thing to try to pick this out, the biggest thing to look for, is the fact that you have 2 things to begin with, which is different than every other type of radioactive decay that we've talked about.